introduce our special guest today, Alexander Abramovich Belavin, who is a founder and a co-founder of a number of constructions in conformal field theory and quantum field theory, and especially string theoretic backgrounds. And today he will present us his work on the conformal bootstrap and the heterotic string Gepner models. So please, Sasha.
Okay, здравствуйте. Good day, dear colleagues, and I'm grateful to organizers for this invitation. The subject of my talk is a new approach to construction of heterotic string theory, compactified on Calabi-Yau manifolds. I remind why we need, namely, heterotic string theory. In the first paper, first work about construction heterotic string theories, the paper of Gross, Harvey, Martini, Crow, 1985. And they construct heterotic string, but it was 10-dimensional models. Then in the paper Candelas, Horowitz, Strominger, Witten, soon it was suggested how to compactify heterotic string theory on 4 dimensions. And they show that to get needed extension of Poincare symmetry until n equal 1, super Poincare theory, we need to compactify the theory on Calabi-Yau manifolds. Then in Gepner work 2 years later, it was shown that it is compactification on Calabi-Yau is equivalent to compactification extra dimensions on
I apologize. Are you mentioning slides or not?
I will do. I will do a few words about history, sure, because it's not here.
Yeah, just to make precise, sometimes it happens. Yes.
I can. Sorry.
It was just
I can.
Everything works.
Okay. Then in Gepner works, it was suggested that to use compactification on N2 superconformal field theory. It made the theory exactly solvable, and in our recent work with Sergei Parkhomenko, we use another approach to construction, n equal this n equal 1 theory, heterotic string theory, compactified on Calabi-Yau equation, but we use some different approach, and it will help, as I understand, to generalize compactification on n equal 1 theory, which is product of several few minimal models of n equal 2 minimal superconformal field series, to generalize it on arbitrary n equal 2 superconformal fields models with central charge 9, which correspond to general set of Calabi-Yau equations of Bernoulli-Hoops type. And a few words why we need heterotic string. We need it to get we need string theory to get theory of quantum gravity, and we need heterotic string, namely to unify quantum gravity with standard models, and also we need it to get we need heterotic string compactified, namely on Calabi-Yau, because we want to get n equal 1 space-time super n equal 1 supersymmetric space-time symmetry. And we can get it's the surprise is the self-consistency of the result demands that the gauge symmetry, the group of gauge symmetry would be E6, which is the only variant to get unified theory. And now I heterotic will talk about this construction. Heterotic string Gepner models is a hybrid of two conformal field theory. In left moving sector, we have n equal 1 superconformal field theory, whose additional 6 dimensions compactified on the product of n equal 2 minimal models of superconformal field theory with total central charge 9. In the right moving sector, we have Bosonic string with central charge 26, whose additional four space-time dimensions, additional 22 dimensions, also compactified on the product of n equal 2 super conformal field theory and also certain dimensions of this 22 compactified on the torus of E8 and multiplied by SO10 algebras. Such heterotic strings get n equal in the result of the construction, in the result of a few reduction, including BRST, GSO, and GSO right and GSO left, and we get n equal 1 space-time supersymmetry, like we want, which arise in left moving sector, and E8 multiplied by E6 gauge symmetry, which arise in right moving part. This symmetry are necessary for phenomenological reasons, the same like we need, namely n equal 1 space times supersymmetry, but not n equal 2, because it will contradict to phenomenological facts. In Gepner work, this requirement was leads to the model which has this symmetries, and but the approach in Gepner book was the main requirement was compatibility, the result with modular invariance. In our work, we show that the same the same result we will get using conformal bootstrap requirements and first time mutual locality of vertex operators and in the left sector with generators of super N1 super Poincaré symmetry. In right height moving sectors we get generators of E6 and E8 multiplied by E8 gauge symmetry, and requirement is mutual locality of leave only such right parts of vertex operator which are mutual local with this generators of this gauge symmetry E8 by E6. And at last, the last requirement is mutual locality of complete vertices, which are product of left and right, galomorphic and anti-galomorphic parts between themselves. Result, we get the Gepner models, and it can be generalized for general case of not only for the product of minimal models, but for general case. But it will be the subject of my next talk. So construction consists of 3 steps. As the first step, in left moving sector, we find generators of n equal 2 space symmetries, supercharges, and set. Then we demand local mutual locality, all left moving parts with these generators. On the second step, in the right moving sector, we find generators of E8 and E6 symmetry, and set of right moving physical states which are mutually local with them. Physical, I mean, Bereste invariant in right. And at last, on the third step, we find such product of left and right moving vertices, which we get above, and which are mutually local to each other. Okay, now what is, as I told, the left moving part in this hybrid is n equal 1 superconformal field theory, which is product of 4-dimensional n equal 1 superconformal field theory, which correspond to space-time sector, whose central charge is 6, and product its product with n equal 1 conformal field theory, which we get we realize as product of n equal 2 minimal models with total central charge 9. And 4-dimensional n equal 1 superconformal field theory is theory of four bosons x mu of z is galomorphic for galomorphic fields, Bosonic, and for Majorana fermions psi mu of Z. And equal conformal field theory for compact sector is for compact subsector is a product of n equal to minimal models of superconformal field theory with total charge, central charge 9. In terms of these numbers, it is, I will not. And we have in superconformal theory, we have two sectors, Newey-Schwarz sector and Ramon sector. In left sector we have Virasoro n equal 1 Virasoro super Virasoro subalgebra whose generators currents of its generators is written here. It is tensor T, which is sum of tensor of space-time. It is written here, and tensor this is tensor which correspond to Calabi-Yau, to product of minimal models, and it is super partner of this, which is looks like this here. And this currents together with can be, in fact, it can be, there exists an equal to superconformal field theory in both sector space-time sector and Calabi-Yau and internal or compact sector, and the currents of this symmetries T and the plus and minus and one parents with dimensions 2, 3 divided by 2 and 1. And they form an equal to Virasoro subalgebra for this compact sector of product minimal models. And what it's important that vertices of this left sector is should admit action of n equal 1 super Virasoro, and therefore in this product we should take product for NS sector, product of NS sector of each subsector, and the same for in Ramon sector. To define, then we can correctly define action of diagonal n equal 1 super Virasoro. We use Berest approach, but it's not very important, or not play very important role. I just mentioned this. This is expression for Berest charge Q, which consists it is ghost C and gamma in in this theory, and this is currents of our algebra in material sector matrices. Means material sector, material sector consists of spacetime sector and Calabi-Yau sector and ghost sector. And Stocky, but it's not very important. Will not play important role. Just it's more convenient to use using the language of vertex operators in this burst approach. Okay, we have vectors operators which correspond to physical states if they are Berestay invariant, and it depends of these fields. Left moving vertex depends of the field x mu, space-time for fields x mu, bosonic fields. H is a result of bosonization of fermions for fermions. Majorana fermions can be expressed in terms two bosonic fields H, whose apparatus space extension is written here, and also we have the field which depend on the fields which describe minimal models. It's here. It's important factor is this exponential factor. It depends. This polynomials depends of the, in fact, of the derivatives of our fields. This factor is exponential of it, and it will important when we will find local modular locality of two vertices. And when we modular locality of two such vertices it's written here. It's written here, and it is the face which we get after finding modular locality is written here. It's expressed in terms of this lambda, and the one charge Q or in ghost sector, and also it depends of the data of internal sector. It's written here. And then next step is finding of massless Berestay invariant vertices. And it's the number of such vertices is finite, and beside the massless vertex operators, we find spinors. This vertex has total dimension 1, PMF squared is equal mass of this states is equal 0, and this vector sigma, two component vector sigma, in this case satisfied to this equation, and it is nothing but Majorana spinors. This vertex operators in spinors in respect to Poincare, to Lorentz algebra, and this is also wave spinors as a chirality, and it is depends chirality depends of this vector sigma, two component sigma. In this case, they are different, and these vertices are not mutually local between themselves, and therefore we leave from this 8. Yes, and it depends also. You see that it depends also of this multiplier, which depends on the data in Calabi-Yau sector, which is described by n equal product of n equal to minimal models. But it's this factor doesn't important when we check to which representation of S Poincare or of Lorentz algebra SO13 algebra. It's important only this part, and therefore it's spinors, and this of different chirality. But they the number is 8 for here and for here, but they do not mutually local in respect each other, and we do the following things. We want to use these vertices to extend Poincare symmetry and super space super Poincare symmetry. And to do this, we need to get only 4 vertices of this 8, which are mutually local in respect to each other. And S plus sigma plus means that here we get we take plus, not minus, is they are mutually local between among themselves, and they are mutually local with this, which where we take minus, not plus, and the integral of this currents of these vertices is nothing but supercharges, which belong to representation spinor representation Lorentz algebra, but and they extend algebra Lorentz algebra until super n equal 1 super Poincare, which we need by phenomenological reason. And then we next step we to get a supersymmetry in the theory, we need to select from all left parts of physical Berstein invariant vertices, those which are modally local with this for supercharges, with this for currents S plus sigma and S minus sigma. And it imposes this restriction on the weights and one charge in this invariant operators. It is nothing but GSO Glotz-Scherk-Olive reduction. And as a result, we get after this reduction, we extend the space-time supersymmetry. And it is here. It is information about the weights, the values of weights lambda in space-time path of vertices. In an S sector, lambda should belong to lattice of weights lattice of SO13, which and lambda should belong to this subspace of this lattice vector or zero sublattice, which such that the sum of this n components of the weights it looks like this vector plus any root of S and Y. In our case here SO13. And there are also two subspace of weight lattice, which consists of spinors and conjugate spinors, which looks like this. And as a result of from the requirement compatibility between this n equal 1 diagonal Virasoro algebra in left sector and GSO equations, which we get before, which arise from locality with this supercharges, we get the connection between data in which is written here between the one charges in Calabi-Yau sector and values of the weights lambda in space-time sector. It's written here. And this completes the selection of subspace of physical left vertices which is consistent with n equal 1 super space-time supersymmetry. Now we take do the same in the right hand, right moving. So in right moving sector, we get the n equal 0. N equals 0 Virasora. We have just usual conformal field theory with Virasora, usual Virasora symmetry, and it consists of this right hand side sector consists of the following parts. It's a space-time part, which is described just for bosonic fields x mu with four-dimensional space-time. Central charge is 4. Then we get other dimensions compactified. The total charge in bosonic parts should be equal 26. So here we get 4. So other 22 central charge for self-compatibility of string theory, we get in the following way. It is product of the bosonic fields which live on the torus of some algebra. This algebra should be taken for self-consistency all construction as algebra E8 multiplied by SO10. So dimensions of torus of this algebra is 8. And this part E8 part described as bosonic 8 bosonic fields which live on the torus of E8. And 5 another bosonic fields is denoted H alpha of 5 bosonic fields. They live on the torus of algebra SO10 with central charge 5. So in result we get 8 plus 5, 13 dimensions compactified on the torus of this algebra, which is product of these two simple algebra. And other, so we get 4 plus 13, it is 17, and other 9 in part equal 9 in central charge correspond to compactification again on the n equal 2 series central charge, which is in this case for this class is a product of minimal models in the right sector, MKE. So we have energy momentum tensor T bar, which is sum of, because we want to get to use n equal 1 Virasora diagonal. In each sector we have some n1 n0 usual Virasora symmetry in this and this, but we want to take diagonal to get physical fields, so vertices invariant field, to get vertices charge, which is defined like integral of this energy momentum tensor, right moving. Okay, we have a vertices approach also the ghost, but it's not very important now. Okay, now we get we get the following massless. Again, we in right moment sector, again we look for massless states, massless Bejer invariant states. There are finite number of subspace, and inside them we found these vertices, which is nothing but a vector in attention in relation to SO Poincaré and Lorentz algebra. We have currents of E8 algebra, which correspond to generators whose integrals are generators of E8 algebra. It consists 8 of them. Looks like this difference 8. Then other is exponent, and k is weights in for E8 just roots of E8 algebra, and the k belong to the root lattice of E8, and it looks like this: 120 this, and 128 this, and plus 8 we get all generators of E8 algebra. So we have we get E8 algebra if we will use this 248 currents, and we can get that satisfied relation in E8. Then we have also currents of SO10 algebra, which looks like this, and there is 5. All of them have like this dimension 1. This is 1. This because the root squared of root is 2, and dimension of this vertex separator is k squared divided by 2, so we get dimension 1. This, and the same here, we have 5 currents of subalgebra, and they looks like this, and we have also 40 other vertices, so they give us generators, integral of them give generators SO10 algebra. But we have also, beside of massless fields, these fields sigma plus minus omega, which are Verstein invariant, which are Verstein invariant, which are massless. Dimension of these fields sigma plus minus omega and sigma plus minus omega dot. The dimension is equal 1, and they belong to a spinor representation of SO10 algebra. 16, not 16, but 32 of this, because of this multiplier plus minus sigma plus minus omega, and where omega is weights of spinor representations of SO10, and it belongs to this irreducible representation, 16 of them. And it is also 16 with omega dot, which consists this for 5 components of omega equal plus minus 2, but sum is equal minus 1 divided by 2 modular 2z here plus. And we can get again that 4 of this, that not 4, but sigma plus omega plus omega, it's plus omega multi-local beside themselves, and they multi-local with sigma minus omega dot, which also multi-local between themselves. And we take them, these vectors, and add to 35 vectors of which give us generators of SO10, and get extension of SO10 to E6 algebra with if we add this to 35 plus 45 generators of SO10, then 32 generators which SO8, which we get as from this sigma plus and sigma minus, and we add one more which consists of the fields which describe our minimal models, and it is one current, and together with this we get all generators of E70 for 78 generators of E6 algebra. It's written E6 algebra elements which correspond to simple roots of E6. Okay, now we get also, until now we get symmetry, we get extension symmetry in right, now in right hand moving sector. And of course we have to impose the restriction on right moving parts for vertex operator. We should require modular locality them with this generators E8 and E6, and we get some restriction. And what is important for physics of elementary particles is that we get which massless representation we get in result. We get gravitation, gravitation supermultiplet. We get vector multiplets which correspond to to E8 and E6 vectors, and we get also material multiplets which belong massless vertices which belong to representation 27 of the algebra E6. It's written here, and 87 bar of E6, which is nothing but the representation which arise in grand unification when we want to understand, to unify our algebra from SU3 multiplied by SU2, U1, and this algebra is some sub-algebra of E6, and this representation used for finding the place in grand unification for quarks and leptons, namely this 27 representation. Also, we get 27, which is written here, and in the result, we E6 was considered even before as possible gauge group for grand unification, and the steps which we get after Higgs effects from E6 standard models, it's written here. E6 contains SO10 multiply 1 and SO10. That's two steps. So we have these representations, and for vector fields, for gravity, and for quarks and leptons, and we have also the fields for describing dark matter, whose take put on the role in, as we know, and found correspond to. Okay, and it is in neutral. It corresponds to neutral representation of sorry, it's not written here. There exists force, so we have gravitational sector, vector sector for gauge fields, 27 bar for quark and leptons, and we have also neutral sector, neutral in respect to our gauge symmetry E8 and E6. Of course, this neutral take part in the gravitation. And now the last step is construction of I forgot to say that when we get E8 and E6, we have to impose a restriction on the right-hand side versus operators, and it's written here. It's called Gepner right equation, and then the last part we have to get it is a restriction on the weights on the right hand side, which appears from the self-consistency, not self-consistency with action of this symmetry, gauge symmetry, E8 and E6. And you see there is a connection between the weights in space in SO10 sub subsector, and Calabi-Yau. There is some consistency. And the last step is to get to consider total vertex operator with product of left and right, galomorphic and anti-galomorphic, which looks like it's written here, and the requirement of, again, of mutual locality and first of all, mutual locality also give some restriction on this, and we, in result, we get the class of the total already vertices which give all states of this model, and this coincide with the set which we get in another Gepner approach when we require modular invariance. Okay, so just a minute. It is about mutual locality, but I will not talk about this, and also this. Here it's written as a singlets, as a case of singlets. If we take Calabi-Yau, which correspond to quintic, to case quintic Calabi-Yau, then we get, in this case, this number of complete singular vertices in this case. So gauge invariance and spacetime symmetry is fixed. Admit only one case, which we use for compactification, namely torus E8 multiplied by SO10. And, but the number of generations depends of the only of the Calabi-Yau which describe, which correspond to the model with central charge 9, and there exist many cases. So it will be interesting to understand how to fix Calabi-Yau, which describe our physics with 3 generations of quark and leptons and so on. That's all, I think. Thank you very much.
Let's thank
attention.
Any questions or comments? Also very welcome. Have any questions or comments? Guys, maybe I can make precise. Alexander Abramовich, can you show when you construct the vertices of these polynomials of the ghosts?
Once again, скажите по-русски. Да, сейчас. Что надо открыть?
Yeah, let me state it in English. When you write the vertices of the polynomials, there is this p ghost polynomial, духовый полином.
Ghost. Ghost part in the very beginning. also
Not
for left.
no,
May I show for left case?
okay, for any. I'm just wondering, this BC.
Because it's more simple for maybe for left. Just a minute.
No, I think that was also fine. I think 3 slides ago, slide 6, I think.
Yeah.
Slide 8, yeah, in this P goes, this beta, gamma, and BC, you split them as bosons and fermions, or because to me, at certain points, they need.
Just a minute. Repeat, please. More slowly, a little more slowly. Repeat.
Okay, so in this P goes, there is beta, gamma, BC.
Beta, gamma.
P ghost, above the first line. Yeah, P ghost.
Here.
Yeah. So,
yes. Yes. Beta, gamma, BC is ghost fields.
so
Yeah.
all of them are ghosts. This is what you consider?
Yes, BC is ghost, usual ghost, which appears even in n equal to n equal to string theory, fermionic. Beta and gamma is the bosonic fields, which was bosonized, which is bosonic ghosts, which arise in equal one. Yeah.
Then this is conventional. This is what, because to me, at different vertex levels, it seemed to me that they are somewhat interchangeable, because beta gamma is usually bosonic and BC are fermionic type.
Yes, right. Yeah.
And okay, maybe more.
Yes, and let me tell again. For in all these fields, which massless fields, which appears how to say, in flat, the role of ghost was this, only this factor, exponent q phi. Here phi is again bosonic fields which bosonize bosonic fields beta gamma.
Yeah, okay, that I see.
It's,
And maybe one more point, but this is rather maybe rather more generic. I mean, do you think in your construction you were having like this product of n equals 2 supersymmetric CFTs, right?
Yeah. Yes.
Right. I'm just wondering, does this construction is extendable if you can consider, instead of the supersymmetric CFTs, like symmetric product orbifolds with higher number of supercharges? Would it have also geometric meaning?
Oh, unfortunately, I don't know this.
Александр Бранович, я имею в виду, то есть там вот эти симметрические орбифолды, если заменять.
No, see, if you talk about symmetry, orbifolds of this orbifolds of these models, which is maybe just explain me what you mean. In Gepner models, Gepner used product of minimal models of
I understand.
n equal to. Yes. Then in what I'm doing now, I understood how to extend it, generalize it on any n equal to models, which is not minimals, but n equal to models which correspond to any Bergman-Hoops Calabi-Yau. And we can take, in this case, we can take a hypersurface or orbifold of this if the symmetry of this Calabi-Yau is larger than minimal. What you mean, this orbifolds?
Yeah. Actually, along these lines, exactly. So
is this, and what's your question? Then repeat, please.
Yeah. So my question is, can you, so like you are having, one can have, like Gepner was considering minimal models, and you said you can have n equals 2. So now my point is, can you get super conformal algebra with higher number of charges? like not n equals 2, but higher, like n equals 4,4 or something.
No, I don't think about, did not think about this. I don't know the answer.
All right, I see.
Maybe I will think.
Okay, let me see if there are other questions. Alexander again.
Okay, so thank you very much.
Вам.
Я не слышу. Есть вопрос звучит, я не слышу.
Не-не, выглядит, что вопросов, наверное, больше нет. И
Ага, все.
все уже выразили
Да,
благодарность. Большое вам спасибо, Александр Абрамович.
да, вам спасибо большое.
Хотя вы еще здесь?
Я здесь, да.
Сейчас я остановлю запись.
Угу.